Following up on de Broglie's idea that the electron might be behaving as a wave, and that these orbitals that Bohr had observed as the only allowable spots for the electrons might be standing waves, that where if the electron is in that orbit, it's in a standing wave where it is able to interfere with itself constructively and make a very high likelihood that the electron would exist there. And if it's out of that orbit, the electron would interfere with itself destructively, and as a result have a very low chance of being in that orbit. Schrodinger came along and he said, let's use the law of conservation of energy and some more wave-based ways of approaching physics to try and determine if that was the case, where would those electrons exist. So this expression is very complicated. I don't want you to get too bent out of shape about it, but the basic idea here is if we have waves and we're doing some more complicated math than what we've learned at this point, this expression would represent the kinetic energy of the electron wave. And this expression would represent the potential energy of the electron wave. And we here basically just saying that our kinetic energy plus our potential energy must go to our total energy. So the idea then is that this function, the wave function, represents the location where the electron is likely to be. That's a slight oversimplification, but in the end, what we're saying is that instead of saying the electron has a specific location, we're trying to say, let's not specify an exact location, and let's instead say, can we come up with a wave that represents where it's likely to be, and then it can exist anywhere within that wave. Now, when we think of wave, we're used to either a one-dimensional or two-dimensional wave looking like this, but part of what makes this equation so tricky to solve is that it's actually a three-dimensional equation, and so we get more complex wave shapes when we solve it. So Schrodinger used the idea of kinetic energy plus potential energy to be total energy, and these waves that represent the locations of electrons, and he did this huge mathematical work solving this equation, and what spat out were some funny shapes. He found that for the smallest orbits, or where the electrons are the closest, they would look like spheres. When the electron waves got a little bigger, they could still be spheres, but some of them would start looking like these. Sometimes these are called dumbbells, or these p orbitals, where there's two spots. And then when they get even bigger, so in size 1, we just get the s's. In size 2, we get the s and p's. And then in size 3, we get a third shape, s, p, d, and that's these shapes. And then as the atoms get bigger and bigger, we get more and more options. We run out of actual elements by the time we hit this F. So while mathematically there are predicted more and more and more shapes, practically for our atoms, we only have these three and one other that's not pictured here, the F. And the F is not pictured here just because it's suitably complicated. And in my opinion, these D's are already getting so complicated that I don't want to spend a lot of time worrying about them. So what you need to know about this for right now anyways is by using the conservation of energy and the idea of a wave where the electron can exist anywhere in that wave, Schrodinger used what's called the Schrodinger equation to predict where the electrons are likely to hang out. Each one of these things, he found out, can hold 2 electrons. So in the smallest shell, we get hydrogen and helium. And then the next shell, because we have 1, 2, 3, 4, 5, 6, 7, 8, in the next shell, we go all the way from lithium to neon. And that's 8 atoms across. So these shells match or correspond with the structure of the periodic table, and as a result explain why the electrons help us understand what the shape a shell might be in to allow it to hold, or let me see if I can say this right. What shape a wave would take on in 3 dimensions if it were to represent the possible locations of the electron around the nucleus.